extent. Okay, a few things to update before we start our lectures. So one thing that we argued last time for the hour of this hint, right? Actually, I missed a very important thing here. So um, so in the assignment, right, you want to prove that this induced action is a faithful action if and only if n is equals to kernel of p. Okay, but what am I proving here is actually this is a group action if and only if n is a subset of curve phi. Okay, so meaning one inclusion here need to satisfy is if this induced action here define a group action. Okay, which is what we argued last time. So the point here is n is in a subset of curve phi, meaning what? You need to send everything inside n to curve phi, but it doesn't require that only elements in n get sent to curve phi. You can send more things to identity. Okay, you can send more. The one that we wrote last time was the curve phi is equal to n, right? Because I just let the closed set n at like an identity. Okay, meaning n equals to curve phi. In fact, you can send more things to curve phi. But when n equals to curve phi, this group action is faithful. So in principle, you can send more things to identity. You can send more things to identity that adds identity. Add like an identity. Okay. In principle, you can. But if you do that, you won't have a faithful action. Okay. Yeah. Yes. So in principle, you can do more. But in that case, we didn't do more, right? Yeah, in principle, you can do more. Okay, in principle, you can do. Okay, I put out this hint. Please go back and read. This is lecture 22. Okay, please read. It's helpful for your assignment. Actually, I wrote down the solution here already, so don't just copy. Try and read it. Another thing is about this unit here. So unit here, I say that the non-zero real number here is a unit in the polynomial ring. Can you find something funny here? Do you notice anything funny here? This third point here. Can you find anything funny here? Huh? Can you find anything funny in this third line here? Anything funny here?
你刚刚不是跟我讲了没？
我现在问他们咯。This one, what's this? This one is element, right? Element of. So this is a set. This is a subset of Rx. So we should use subset. Okay, we should use subset here. So because in general topology, sometimes you need to deal with element in terms of set. So you need to be careful whether you see it as a set or you see the set as an element or you see the set as a subset. Okay, it's very important. So here just say that everything inside here is a unit inside Rx. Okay. All right. If you notice in my previous year notes, you will see some notation like this. FP. Okay, so what's FP here? So FP here is making ZP into a field. Okay, where P is prime. How to make ZP equals to P field? Whenever we discuss about this kind of general statement, right, you should pick a P for yourself. You should pick a P for yourself to think about it. What kind of P you can pick? For example, Albert, what prime you can pick? Great, good. So in Z3 got how many things? Huh? 3 things. So 0, 1, 2, 3. Okay. So how to make, sorry, 0, 1, 2. So how do you make ZP into a field? Z3. Is Z3 already a field? Hmm? How to be a field? Yes, why? 0 got inverse. Huh? What kind of inverse? There are 2 inverse you need to talk about, right? Additive inverse and multiplicative inverse. Huh? 0 got what? Got multiplicative inverse or not? 0? Huh? 0 divide 0 Huh? 0 got additive inverse or not? Oh, additive inverse got, right? But multiplicative No. 0乘0等于0又怎样？我要0乘0等于1哦。我等于1。E is the multiplicative identity, right? So can you multiply anything here or not? No. Then is this a field? You sure? So what's the definition of field? Field says what? What's the definition of field? A ring where 1 is not equal to 0 and in each every non-zero, just non-zero element is a unit. Okay, just non-zero element. So 1 has inverse or not in Z3? What is the inverse of 1 in Z3? 1 times what equals to 1? 1, no? Okay, 2 got inverse or not in Z3? Huh? 2 times 2 is what? 4. 4 is 1 mod 3. Okay. Yeah. Okay or not? So that's why I wrote where I wrote. So I wrote here, right? ZP equals to FP here last time. Okay. Yeah. So if I write FP, you think of it as a field. If I ZP, usually just a ring, but it's the same thing. Okay. Yeah. But have to be prime. Otherwise, if it's not prime, not every element has multiplicative inverse. Additive always got, not multiplicative prime. Okay, for example, in Z6, Z6, 2 doesn't have the multiplicative inverse in Z6. Only the number that is co-prime to n, okay, Zn such that, so that it has a multiplicative inverse. Okay, this one we briefly talked about it last time. Okay, I think so far is this. Okay, another thing asked by Lydia, right? So Lydia asked, what's the usefulness of group action? What do you think? Anyone know how useful is group action is? Anyone know what's the usefulness of group action? Well, I mean, one usefulness of group action is we call the faithful action. Okay, the faithful action. That's why I asked you to do a lot of questions on this kind. Faithful action here. So faithful group action says what? The only thing that acts like an identity is identity element in the group. Okay. So let's say, let's say you have 2 elements act the same. Okay. So what's wrong about it? What's wrong about it is let me think. So let's say your action is not faithful, meaning there's another x. So x is not E, but x act like a identity. What happened here? Meaning you cannot differentiate these 2 group elements, okay, by looking at the group action. So for example, what? So Lydia say use baby language. So think about a globe. You know what's a globe? What's a globe? D2E, right? How does the globe look like? Round, right? Okay, so it is round. So you can rotate it. Okay, so you think of it, we do two rotation. Is it another rotation or not? If you rotate a certain degree or certain angle, is it still another rotation if you rotate twice, no matter how you rotate it? Right or not? So rotation is a group, form a group because it's close, right? Right or not? But you can see that after you rotate, right, your globe change. Right or not? Maybe China on this side before you rotate. After you rotate, China become the other side. Okay. So what two rotation make the same globe? Right? Maybe 0 and 360. Right or not? You rotate a full turn coming back to the same place. Okay. So then in a different degree, you can see that with different degree of rotation, they give you the different position of globe. Okay. For example, you rotate 10 degrees, you rotate 20 degrees, you will see that China on a different side. Okay. So you see, just looking at the globe, you will know that these two rotation is all are different. Okay. So if it is faithful, only identity X identity, meaning just looking at how you take group element acting on your set and then look at how the set changes, then you can differentiate your group element. You know? So you will remember that, oh, rotation with 10 degree is China on the left side. If I rotate 20 degree, China is on the right side. So you just remember how the globe changed, you can differentiate your group elements. Okay. Yeah. Yeah. Because sometimes a group can get really abstract. So you maybe there's no natural symmetry for them. So you need to find some other set to differentiate these group elements. Okay or not? Yeah. Because in principle, in principle, how? In principle, yeah, in principle, you can write down a bunch of generators and then a bunch of relation. And then who knows the relation is redundant, or who knows you write too much generators right in your assignment. You can reduce generators, right? Okay, yeah. So group action is another way to study them by looking at how the group changes the set. Okay. Yeah. Okay. Let's continue with our ring sorry, ring business here. Sorry, I haven't finished marking your assignment. I'm still working hard.
deadline.
Your deadline. Welcome. Okay, well, wait, okay. 公平. Okay, it's okay. Okay, next one. Okay, let's recall again. What's polynomial ring? So let's start with defining what's a polynomial with coefficient in R, in a ring R. So what is it? This is just a finite linear combination of powers of the variable x. And then we will call these powers of the variable x as monomial. Okay, monomial. Monomial in x, sorry here, monomials xi. So in our case, we just study finite linear combination. If it is infinite, we have the different names, right? If infinite, we call it what? Power series. Okay, formal power series. If infinite in two ways, we call it Laurent series. Okay, so we only study finite here. Okay, if you collect all of them, this is what we call this R adjoint X. So you must remember this notation. Where you keep using this notation throughout the course. Okay, until the end. Rx, R adjoint X here. Okay, set of these things we call Rx. Or we call polynomial over R. Okay, please familiarize yourself with this over adjective here. Over is to describe what's the coefficient you take over what? Over what? Okay, something over what? Over complex, over real number, over integer modulo, and over anything. Okay, over is for coefficient. And when are the two polymers equal? Basically, you just compare all the coefficients. Okay, just compare all the coefficients. For example, 1 plus x is not equal to the 1 plus 2x. Why? Because the coefficient for x is different. One is 1, one is 2. Okay, and then linearly independent. So this is very much like your linear algebra. If you have a linear dependent relation over x, okay, over x meaning you can take coefficient in x, okay, such that the sum of them is 0, then meaning that only the 0 coefficient will satisfy this. Okay, if there's no 0 means what? For example, r1 plus r2 equal to 0. Okay, let's say s1, s2 is 1. Meaning what? r2 is the negative 1 times r2. Okay, so you can multiply negative 1 to r2 such that you get r1. So there is a dependence there. Okay. 对不对？对不对？如果你要跟一个人没有关系，你是不是要切断所有的关系？对吧？全部一定要是零啊！你如果要跟这个人没有关系，你要切断它。OK，一个不为零都没有用。OK，你要切断关系，就是全部的生成。OK。Okay, today we will go through some slides. I don't want to copy because these definitions are quite sad. Maybe I'll give examples. So next is we define what's the degree of a non-zero polynomial. What's the degree of f? It's the largest integer n such that the coefficient an of xn is not 0. Okay, 有一点抽象. Is it a bit abstract or not, this definition? 会抽象吗？这个 definition 啊？不会 ，OK， 李佳说不会，这样你要给我们一个 example 了。来 ，Let's give one example， 不然我考你好不好 ？So let's take f x equal to let's say 1 plus x 100. So the question is, what's the degree of f? 100, good. So this is the largest integer n such that the coefficient of xn is not 0. The largest one is 100. Although you can see x1, but you have 100 there. Okay, everyone follow? Can okay. So far so good. And then polynomial of degree 0 is called a constant polynomial. Okay, where the degree 0 is constant polynomial. So what does it mean? Degree 0. So for example, fx equals to 1. Okay, because 1 is what? 1 times x to the 0. Okay, and then the highest integer such that Sn is not 0. Sn is coefficient of Sn is not 0 is x to the 0. Okay, so that's why we need to introduce degree first so that we can talk about different degree. And other than degree of function, we also can define the degree of a monomial here. So degree of monomial is easier. Just say as the power of x. So a bit different, degree of a monomial is just refer to a single x to the some power. But degree of degree of function, you need to look for the largest one. Okay, yeah. So there's a subtlety here. Can follow so far? Just terminology. Okay. Next you can consider polynomial in variables, multiple variables. Okay, x1 out to xn here. Okay. So similarly, you can talk about degree of such monomial, okay, product of such sj to the ij, okay, sj to the ij here. So what's the degree of this polynomial? It will be the total degree of the power that xi takes, okay, I1. And then these polynomial will form this ring, x1 to xn. R adjoin x1 to n. Okay, so for example, let me give you some examples here. So what elements inside here, for example, x1 times x2, right? Or x1, x2, x3 squared plus x to the n to the power 4, something like that. Okay. Yeah. Okay, now all the definition can extend. Any question? So far? Okay. Just definition. Later we'll do some fun stuff. Okay. Next part. I want to define what's called a leading coefficient or leading. So let's tell us something about the coefficient. So why the coefficient is called leading? So the non-zero coefficient of highest degree monomial of a polynomial is the leading coefficient. So for example, let me give you an example. So what's the leading coefficient? Let's say of a polynomial 1 plus x squared. 1, right? Okay, because you look for the highest degree polynomial first, and then you look for the coefficient. Okay? Yeah, so if I make it into 2, okay, if I make it into 3 here, then we'll get 3, the highest one. And if the leading coefficient is 1, then we'll call it a monic polynomial. So can you give me an example of monic polynomial or not? X squared plus 2x plus 1, good. So why is this monic? What is the leading coefficient here? 1. Okay, it's in front of x squared, and then it is 1, so it is a monic. Okay. Right. Next, we're gonna prove that Rx form a ring, commutative ring structure, so that you don't need to do in your exercise already. So we prove that Rx is a commutative ring. So how to prove it? Let's take two polynomial here. How do we add them? How do we add them? We just add by coefficient, okay, in the appropriate power. How to multiply them? Just distribute, okay, just distribute it. But in the class, in the assignment, I put a different ring structure, right? You do composition there, okay? But in polynomial ring, you just multiply two polynomials together. Multiply two polynomials together. You see, what happened to the coefficient here? Okay. For example, the coefficient of x squared. How do you get x squared terms here? After taking product, how do you get the x squared terms here? What is the possibility you can get the x squared term? You can take the x squared term for fx, multiply the constant term in gx. Or you can take the x term from fx, multiply the x term in gx. Or you take the constant term in fx, multiply the x squared term in gx. How to describe them? This is when the power of x, or xi times xj, such that I plus j equals to 2. Okay, so all the possible way that you add to 2. 0 plus 2, 1 plus 1, 2 plus 0. Okay. Okay, continue. So, how about R here? So R here without the monomial will become a subring of Rx here. Okay. How do we see them as a polynomial? We see them as a constant polynomial here. Okay, we see them as a constant polynomial. In particular, we see them as R times x to the 0. Okay, R times x to the 0. Okay. Yeah, so it is a subring. Okay, so you can check whether what do you need to check? If I define like this, tell me what you need to check. For addition part, what do you need to check? It forms a abelian group structure. Okay, is it abelian or not? Why? 反过来加变成什么 ？G plus F 会变什么 ？B0 plus A0. But why is it A0 plus B0 equals to B0 plus A0? Because 那里给我们生的，你错了，考试会变哦，那个 ring。OK， 什么？ Whose addition here? This addition here refer to whose addition? R. Okay, because R is already a ring. Okay, yeah, R is a ring. Don't think of this as a real number. We can change this ring. Okay, as long as it's a commutative ring. Okay, this is a billion group. Okay, next multiplication. What do you need? What's the multiplicative identity here? What's the multiplicative identity? 啊？什么？什么？什么？啊 E, right. Is one a polynomial or not? One is a constant polynomial. Okay. One exists or not? Why one exists? Where does this one come from? Good. Because R has one. Okay, so you need to realize on the coefficient ring actually. Okay, you need to rely on the coefficient ring. Otherwise, you don't have the one. Okay. What else you need to check? I think that's all. Others should be easy to see. Yeah, go back, try and write it out. Okay, next. Division with remainder here. Okay, so actually, if you take the monic polynomial, you can do a division of f with any g. Is it any g? Yeah, any g. Okay, any g you like. So remember, the first time we started this chapter, what I say, polynomial ring is like a integer. Okay, like an integer. So you also can do division here. Have you learned long division in your before you come to university? 有没有？有没有？来 university 才学？小学哪里有哦？
玩号码号。
对呀、号码啦，对呀、对呀、我说 long division 啊，你3年级会这个
我们几个号码吗
？AG OK yeah 号码 yeah 号码 I mean what I meant is for polynomial. I think I first time I see this is in A level. Yeah, my A level. Okay, so do you know how to do this? Huh? Okay, I mean, do you know how to do this? Okay, so what do? You multiply x squared so that you get the first term, right? To cancel. And then you want to cancel out this term again. So you multiply by 2. That's 2. And then what do you left? Yeah, x plus 6. So you cannot divide anymore, right? Yeah. Because we are polynomial ring, we don't have negative power of x. So what do we get? 2x plus 2 is equals to, sorry, the other way around. x4 plus x plus 2 is equals to x squared minus 2 times x squared plus 2 plus x plus 6. Okay, so here is the remainder. Then x squared minus 2 is a quotient. Okay, so the claim is these two things are unique. Okay, it's unique. Not that we are using monic polynomial here. Otherwise what? Otherwise, if I put a 2 here, imagine if I have a 2 here, what do you need to put? You need to have a existence of half. But this is not always true in ring, because ring doesn't always have a multiplicative inverse. Okay, so that's why this proposition here start with a monic polynomial. Okay, so monic you don't need to care about taking inverse, multiplicative inverse. Okay, otherwise it will be a trouble. For example, I mean, if you modify this I to a field, then your f no need to be monic because you can always take multiplicative inverse. Okay, no? You want him? Any question? Yeah. 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 Uh, wait. You mean divide by 0? I think this obviously cannot be 0. Yeah. 有人骂你们 common sense？ No, I mean, yeah, 0 is not a Morley problem though. Yeah, it's the leading coefficient is not 1. Yeah, leading coefficient is not 1. F F and G 也是任意的 ，F and G 都是任意的。Yeah， 看你怎样定义 ，true。Yeah. So if I write this form right, so we assume that F is the degree of F should be a little bit smaller than G. Otherwise, if G is a smaller degree of F, what happens?
Q is 0.
Yeah, Q you can take 0, then remainder is just the G. So yeah. Okay, any question? Question? 来，问题啊。Hey, please ask like what I told Ian yesterday. So make sure you ask during the class. Otherwise, you go back and think. You spend a lot of time. You think out of nothing. Then you blur, you depress, you do everything. So you make sure you depress here, ask here, confuse here, make mistake here, go out. No need to make mistake. Okay. Yeah, make sure you ask. 不要害羞因为我差不多就要看不到你们了所以有机会快点问。Okay, yeah. Okay, so moreover, the last line here is if F divide G, meaning what? The remainder is 0. It's like what you do in the Z, right? Yeah. There's no remainder if you can divide. Okay. So I make a remark here, the Morley condition is crucial for the ring you are working at. For example, they don't have a G and R such that 3x equals to 2x times G plus R in Zx. You cannot invert 2. Okay, you cannot invert 2. So you cannot create 3. Okay, there's no 3 over 2 inside Z. 有吗？有没有？谁的 integer 里面有3分之2、2分之3？直线啊。Okay. Okay. So what's the corollary here? So the corollary here is division with remainder can be done whenever the leading coefficient of F is unique. So as long as your leading coefficient of F is unique, you can do division with remainder. Okay. Or if your coefficient ring is a field and F is not 0, you also can do it. So this is what Lydia asked. It's a corollary here. Okay, in particular. So F cannot be 0. Okay. But in this case here, I give another example here. You see this element here is not monic in Z mod 3Z. But I still can do division with remainder and Y. I give me reason why. This is not monic, right? The leading coefficient is 2, not 1. But I claim that I still can do division with remainder Y. In Z mod 3Z X. Is a field so? It's a field so? Who going first? The 2 going first. Okay, so basically you can multiply by 2 to get rid of this 2 here to become 1. And then you can go into any coefficient that you like. Okay. Yeah. Whenever you go to 1, you can get to the other coefficient. Do you know that? You know? You know? 1 can get to the other coefficient. You take any R times 1, you'll get R. Okay. 这样懂，可能又不懂，这样看你们。Continue first. Okay. So another corollary is if you take a ring, okay, consider Gx in Rx, the remainder of the division of Gx by x minus a x minus alpha is g alpha. Okay, because x minus alpha divides g in Rx if only if g alpha equals to 0. So do you know what this means? So if you try to divide a polynomial with x minus alpha, what's the remainder there? The remainder is just the substitution by alpha. Okay, I'll let you think about 2 minutes or 3 minutes. Try and prove this or discuss with your friend. See this fact. This fact is really important. Okay, later I'll show you an example after proving. 想一下这个东西。This is a very important fact here. How to get remainder? No need to do long division. Just substitution is enough. Alpha here is a elements in ring. Okay. I'll give you 2 minutes. Try and think about it. So one hint I give you is just now I didn't tell you one important thing about remainder. So the remainder, for example, 6 divided by 4. 6 divided by 4. What's the remainder? 2. So the 2 is always less than 4. So in this case here, the remainder, the degree of the remainder should be always less than the function f. Okay, the one that you. Okay. So what's the key here? Well, obviously you start with division remainder, division with remainder. So how do you write it? You write it as gx equals to x minus a times some quotient plus some remainder. But the remainder here is very special. What's the degree less than x minus alpha? X minus alpha is already degree 1. So 1 degree less than it is just constant. So that's why I put r here. There's no rx anymore. It's r. Okay, so, well, I mean, what's this constant here? So if you substitute alpha into this equation here, what do you have? Alpha minus alpha is 0. 0 times qs is q alpha is 0. So r equals to g alpha. So let's try one example. This is a very interesting fact here. So you need to appreciate this example to learn this corollary here. So let's try maybe this one divided by x minus 2. Okay, if you do the long division, what do you get? X squared minus 2x. Hey, sorry, too many x only. And then 3x minus 2. And then plus 3. 6, you get 4. But by the corollary just now says what? If you substitute 2 into your gx, do you get 4 or not? Yes, so fast. 4加2减2, you get 4. Meaning you don't need to go through these long division anymore. Just do substitution. Okay, no? Yeah. Okay. Yeah. So what's the proof here? The proof here is really easy. I use division with remainder. Okay. So. Okay. 全部人看到吗？可以吗？不需要做 long division 就可以找到 remainder，是 substitute 好了。OK， 有问题吗 ？Any question？ 有问题吗 ？Before we jump to next part. Any questions so far about polynomial ring? So one thing you need to remember about polynomial ring is you can do division with remainder. That's all. That's all. Okay, if no question, Because next part is a new thing, so we can take a break until 555. Triple five. 你要抄哪里？
听众的会今天要累一下是吗？
要
让我累一下是吗？上节课打的东西太少了，所以今天这样写都不行，就直接把它放出来，来让我多打一点是吧？
因为好像有一大长的东西我要搞掉。
好，那我刚忽然想到一个问题，
什么问题？
如果是这样的话，VP 难道不是一个 complete order 的 field 吗？
对，对了，对。你要放什么 metric 先？
不是，就是 SP。
我知道。complete 要有那个长度，要知道怎么量它们之间的长度。要 form 一个 metric 先，你要讲 metrics，你要考虑 metric space。
哦，
它跟 R 可能不一样的 metric，可能那个不是 metric 在它上面吧，应该。
0到1是1，0到22，可以吗？
你要 check 一下有没有 triangle inequality 哦，最重要的。
我不能用那个 last 那个什么 list up list up bound 吗？
不一样啊，不一样吧？哦，我知道为什么你讲那个东西了，因为确实哦，这个 list up bound 其实，所以 that's why 我强调要用那个每一个 code sequence 有一个 limit 来看，因为那个就是 complete 的
那不是等价吗？
的意义啊，
应该不是等价。
但那个世界是等价，跟其他世界。complete 的定义是 every code sequence 啊，开始。
那个不等价吗？
I mean 那个只是在 R 里面的世界，
那其他地方能不等价？
其他世界，啊 every non-empty subset has a list of above。
对
depend 我不懂还没有想过。
首先它肯定
要想
012应该是 order 的对吧？它又是别的，
可能是 config 的问题哦，应该
还是 order 的问题。
懂因为不懂啊，我有那个我有 reference，他说全世界只有一个吧，
对啊，我也知道，感觉应该全世界只有一个，但是
有一个 reference，
但是我觉得
可以去看一下
complete order field，
可以去读一读。金鱼在吗？金鱼。子豪嘞？子豪在吗 ？OK， 对，一层 OK， 我没有认错人了，行。
Wikipedia 说每个 order 的 field 是 complete 的，如果它的每一个非空子集都有 list up bound。所以我觉得如果这个地方出问题了的话，它有可能是 order 的问题，我觉得更可能。
对啊，
有可能。
interesting。哦，没有，太快呀，我抄不到不行，
我觉得这东西很狭义，
快点再抄
不需要什么都抄。
我喜欢抄。
可是我如果方向写错了，你抄错，
我就会问你哦。
你会问我 OK， 但是你当下呢？你当下讲，
就是我先抄先，然后我听你讲。
OK，然后你会讲个，
你讲的对，我就觉得对，
我也会写
但，是你写错，我就可能看不到。
但是我
OK，
可能有些东西不会写的那么长。然后如果我看到你有错，我直接给你来 Q 一下。
是一个 ring 里面的每一个 element 不一定有 multiplicative inverse。
对啊，不然
it is true 啊，因为还没有，因为0都没有 multiplicative inverse。
但是如果零
field 的
零肯定没有
非零元，
零肯定没有。
对，但如果是 field 的话，它的非零元素在吗？
金盆在吗？刘金盆，
他在
哪里？在哪里？
它现在应该
是其中一种 ring。
对啊。
哎，我想找2个人，小月和红瑞，过来一下。小月跟红瑞。Hello，对，哎，我想问一下，你平时
比较厉害的 ring。
课业还好啊？你觉得你有时间吗？
也许有。
也许有啊。OK，
因为我不要上当。
对，我知道我找过他了，但是我想要再重用你一点。其实，我觉得你很多潜力，呀，可以发挥一下。
很像老板讲的。
画大饼，
画大饼。
因为他们比较我找你是因为我看你的答案记得每次都加一点修改。
他的如果按照这样子的批不出来这个 order 的 field，
不能比如说我班上不是一些，
如果按照他刚刚说的话，我觉得 AP 不会是一个常识，或者 FP 它是一个可以到 order 的 field，
就是那些稿本来不能写好的。
但是
比如说
complete order 的 field，理论上来我们就说我的定理 complete order 的 field，
比如说这样子啊，我说 uni 过后就 example 嘛，对不对？但是我没有证给你看他们的 multiplicative inverse 是什么，能不能写一个完整的答案？
所以他刚刚在跟我说这个东西可能是要去到那个
这样的话你可以帮忙他打，你就不用打，要打还是要写啊？如果做这些练习，写给你打还是他自己打？
可以讨论一下，
可以讨论一下，可以吗？可以吗？呀，我安排他给你 ，OK 吗？呀，这样他的答案其实很好，他每次的3门答案都很好，呀，所以应该就会准确性很高。OK，
所以我觉得问题
呀，
这
样的话，我叫他跟你联络，你认识他吗？
我认识。
你才会手吗？
还
上手啊，这样我就叫他联络你了。OK， 好，谢谢。
必要的他已经是必要的了。
OK，说你之前有在做阿听嘛，对不对？还在做嘛？还在做。OK， 你是自己做还是有上网找？好像没有这样 ，OK， 可以，没问题。好，但是我还想让你帮他一下。
我很 boring 啊。
很 boring， 但是很重要。现在很
重要，真的很 boring。
OK， 现在他打的部分是 Chapter 0，就是为了读懂这个 AA 的东西，前置的一些知识是什么。他已经打一部分了，不知道你看过吗？没有，你没有看过？还没有看过你打我快母的了，OK。但是我觉得它不够完整，我要再把它完整。然后我已经制定了一些 highlight 的部分出来，然后我们现在要决定一下把哪一些部分打出来就好，就是有些 proof 可能不用，或者有些 theorem 不用，但是主要的一些 theorem 一定要在 such that 他们读 AA 的时候就不会卡。OK， 知道大概我讲，Yeah， 如果能的话，我就把你拉进来，现在 OK 拉进来，我也让你去读一下，我已经让他们去读了那些 highlight 的部分。然后我们下个拜二下个拜二可以吗？有空吗？下个拜二
我是说 OK 了。
下个拜二
拜9点啊？
什么叫9点哦？
拜二不是？
就是我 office hour。
拜二不是上到9点咩？
没有啦 ，office hour，office hour， 在 office hour 的。对啊，在我 office hour 的时候，那我们来讨论一下，解决掉什么要打，然后就去打吧。
重点是在他的 proofing。
我知道，就我们讨论了，看要留什么 proof 还是不要留了。但是最主要是我们要把一些重要的结果、重要的 theorem 把它写下来，然后或者重要 definition， 比如说什么 complex 我们中间不时会用到，然后或者 matrix 关的东西OK 吧？
我觉得出招的。
阿听的那个，我觉得我可能放重点在其他大哥那边。
如果是
你也可以做，但是就
我感觉会这样。
我问一下他们。Hello. Hey, Kamke and Kamke. Are you guys still doing the acting stuff? Huh? Not what?
可能会可能放哦，
对啊，
Are you trying to do?
往后调。
Yeah, you can try to do. Yeah, try to do. Yeah, try to do.
继续。
You can. You know that we already upload something now on the extra tutorial session. We have uploaded on the Moodle. Yeah. So you can see where you can pick up from what is not ready yet. You can pick up from what where we stop. 啊，他可以，他没有在做啊，很麻烦。现在做主席啊，蛮好做的。要不然我帮你做。你怎么做？说说看。招东西。好，旁边你，哎，快点！你们的主席现在有难，有难是不是要同当？那要帮他工作啊，他没有手没有脚，他就挠啊，他就不是没有，你应该讲没有，他才可以帮你，他没有，没有人帮他跑啊，没有帮他去做事情啊，啊，要帮你们的主席没刷，
摇，
是你们投出来的吗？他们，你没有投嘛？你没有投啊？你不懂，谁有投啊？谁投出来了？你投了呀，投出来了要去帮忙一下。
不太想的。
哦，你进过 VT 了啊？周琦进过 VT 了。那看一下。
他讲 OK 吗？
有。
我盖过给你了。
所有有兴趣的可以去帮忙一下。你们做什么工作先？
做一个 action 在 group。
我知道。
一个。
比如说要帮忙做什么？
就不用一个。
OK，publicity。
就那个 Facebook 的话，我们做一个
微信啊。
我们做一个 action 在那 group， 我们拿一个 element 来看，我们就可以概括它，它的 element 会怎么变这样。
有兴趣的话。
哦。
我想。
可是要是它不飞，东西会变另外一个，会有两个东西变同一个东西。
稍等一下，我的时间到了。
什么意思啊？
FP order
我看不懂。
FP 不 order 的。FP 不 order 的。
不 order 啊？为什么 order 不了？
你去看 order 的定义，它要有一条是要如果 A 小于等于 B， 那么 A 加 C 小于等于 B 加 C。然后你去看0，比如说0小于等于2，但是你加了1以后，它变成了2和0以后，它不是小于等于1，所以它不 order。
你这做我们的 division of remainder can be done whenever the coefficient of f is a unit.
It's a unit 就是说它有 multiplicative inverse。哎，这样我不是就可以把它变回1哦？然后变回1过后，我就可以transfer所有的 R， 然后我就会拿到我要的 R。
它就有两个东西。
我想不到。
哎，两个东西。
哎，刚才不是有一个
是如果 faithful 还是不 faithful？
因为它这个 unit 嘛。
为什么 faithful？
然如果我有一个 polynomial 是 x cube， 然怎么呢？怎样办呢？我就乘1/2，我就可以拿到2/2 x， 我就可以拿到 x 就拿到。可是1/2在这边是2。
会有两个东西变成一个东西。
啊。
那么我们
那你不是还得定义？
被脑残了。但是我们这里放一个2。
没有用，是要这边不毛病。我要 start 了。
所以这边是可以 monomic 的是吗？啊，这边是可以不 monomic 的。
这边是可以不 monomic， 这边是可以不 monomic， 除的那个要 monomic，
除式要 monomic， 被除式可以不用。
当然，
我想通了，我知道，因为如果除式有不 monomic 会有。
Okay, so be careful where you put the monic thing. So the monic is the f that you try to divide the other polynomial. Okay, so let's continue. So we will finally reach ideal and homomorphism. Okay, so like a group, I start, right? So in group, we have a map between groups, right? In ring is the same. We also have a map between rings, which we call the ring homomorphism. Okay, from R to R. So what does this map have to satisfy? So this map have to satisfy satisfy what? It's a map such that for all A, B in R, phi of A plus B equals to phi A plus phi B. So it's a group homomorphism first. And then it is also phi AB equals to phi A times phi B. So it's respect the multiplicative. And there's one more thing we need to specify here. Okay, specify here. We send the multiplicative identity to multiplicative identity. We don't need to satisfy, we need to specify phi 0 to 0. Do you know why? Because the group homomorphism here will imply that. But unfortunately, this preserving ring structure here won't imply phi 1 to 1. So that's why we need to add this extra condition. Okay, so we need to say this explicitly. So what sort of ring homomorphism you had? So please go back and check. So try and show them yourself. So for example, we could have a map from Z to ZP, okay, where P is prime. So what's this map? Can you guess? Send N to where? Send N to where? N mod P. Okay. So you need to check, is it a group homomorphism? Is it group homomorphism under addition? Okay. Does it preserve the multiplicative structure? Okay. Does it send 1 to 1 or not? Can you quickly see, does it send 1 to 1? What is the multiplicative identity here in Z? 1. 1 mod P is what? 1. So it is the identity in ZP. Okay, the other one I'm more readily to show you because we're gonna use this a lot. So this is a ring homomorphism that we call evaluation of say real numbers or nouns. So it's a re-evaluation map here. So this is very important ring homomorphism in our topic here because we're gonna play it a lot of time. So let's prove that this define a ring homomorphism. So this is a map from polynomial ring over R to R. Okay, so can you guess what happens here? Evaluation. Can you guess? So I fix an A in a real number. So what can I do to polynomial? Hi, Yushen. Give me a polynomial. What can I do to it? I give you a number. I give you a polynomial. So what can you play with these two things? Substitute. Okay, so how do you substitute? You substitute x as A. Okay. So you will add up a real number here. Okay, so let's prove that this is a ring homomorphism. Let's prove this. This is more important and more interesting. So first, we need to show that this respect addition. So let's take two polynomials and add them together. So to do that, we need a general form of polynomial. Okay. So I write px equals to c0 plus c1x plus dot 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 plus cnxn, and then qx equals to b0 plus b1x plus dot 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 up to bmxn. Okay, potentially they are different polynomials. Right. So what to do here? So what do we want to show? We want to show that A of P plus Q is equals to A of P x plus A of QX. Okay. In other words, what does it mean? We want to show that A of P plus QA is equals to PA plus QA. Okay, so let's see. So let's write down left-hand side first. Left-hand side is P plus QA. So meaning what? You need to add up all the coefficient. Okay, C1 and then B1. X become A plus dot 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 up to where? CN ah? Can it be BM or not? BM? CM or BM? CM or BM? 哎呦，真聪明。So without law for generality, you can assume that let's say m greater or equal to n, then we can add up to cm. Okay. So let's say m is 4. So let's say, for example, m is 4, n is 2. Okay, so what is C3 and C4 then? You should take them as 0. Okay. Okay. Any question? 有问题吗? So the issue here is we scared that m and n, the power is different. So how to make them the same? You just add a bunch of 0 terms. Okay, you just add a bunch of 0 terms. Okay, 吗？明白吗？ Maybe one of them is 1 plus 1加 x 加 x square， 还有一个1加 x， 怎么变成一样的 degree 呢？1加 x 加0乘 x square。Why? Because we want to have a collective way to talk about these coefficients. Yeah. 哪里啊？鸡蛋啊 ？What do you mean? What do you say? What are you trying? 没有假设。因为我要给你看为什么without law of generality 发生在这里。就是说，假设，谁给你一个很完整的 example 给你看。Right? So an explicit example, px is 1 plus x, qx is 2. Okay, so how do you make them the same degree before adding? So you add to q by 0 times x, so that p plus qx is equals to 2 plus 1 plus 1 plus 0 times x. Okay. 可以吗，华兴？华兴，好像你又变黑了。华兴每次读 AA1 的时候，他会变黑的。OK 吗 I add an extra 0 so that they have the same degree to compare. Same degree to compare. Okay. Any question? Other question? Hey, this is a very explicit example. If you cannot follow, you definitely have to ask, because there's nothing more to worry about. Okay. Continue. Right hand side, what is it? PA plus QA. You get C0 plus C1a plus C2a squared up to Cm a to the m, and then on the other hand, you get B0 B1a plus B2a squared plus until Bn a to n. Okay, so is right hand side equal to left hand side or not? Equal or not? Why is it equal? By what? Distributivity law. Distribute, right? Oh, not just distribute, you need commutativity law also. Because after you distribute, what do you have? You have alternating C and B. But in the right hand side, you need to group all the C together and then you group all the B together. Also, you need distributivity and commutativity. Okay? So, left hand side equals to right hand side by distributivity and commutativity. Okay. Okay. Yeah. Right. How about next one? We want to show it. So for the second one, we want to show that APX QX equals to APX times AQX. Yeah. 哪里？啊？什么东西写错？对，这样子哈。写什么？什么问题？ I mean, well, I mean, we can do like this. So, yeah, 加等于零，那个零是夹在中间里面。I mean, 夹在中间里面。I mean, well, I mean, 哪一个东西开始等于零啊？其实是 n 加一开始就等于零啊。n 加一。Okay, let's write down a bit careful here to tell you what is going on. So plus 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 until Cn a to the n plus Cn plus 1 a to the n plus dot 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 out to Cn Cn times am, but we know that all these are just 0. Okay. Okay. Yeah. So maybe we also can, without loss of generality, just assume that these two polynomials have the same. I cannot say they have the same degree, but we can express them in terms of the same polynomial. Just that the coefficient could be 0. Okay. Yeah. Okay. Yeah. So without law of generality, maybe can appear faster earlier. All right. How about this one? How about this proof here? Okay, how about this proof here? So this proof here is not too hard also. So on the left hand side, what do you get? These are the sum from 0 to n plus m, okay, of S, K. But how to write the sum here? Still remember just now what I told you? You need to add up all the coefficients such that they sum out to K. Okay, depend on which K you look at. I look at all the ij such that they sum out to K. So this notation here is a bit weird, huh? There's no starting and ending, just that all the ij such that you sum to K. And then you evaluate at A, right? So you need to change your X to A. But what are you really doing is you just multiply the polynomial. Okay, so it's really the same as you. Okay, so let's write out. So here is a sum of K from 0 to, let's say, P is M or N. Oh God. And so this one is N of C, right? CK of AK times the other one, let's say use j from 0 to m of cj times aj. Okay, so these two should be the same. Can you recognize it's the same or not? Because previously, 什么题？昨天不是 B 讲什么？哦，sorry，是 B。Okay, yeah. So it's the same calculation, right? Because previously you just compute by x, but here you compute using a, so it's the same. It's the same calculation. 明白我讲什么吗？来给你一个 example， 很快的 example. So for example, 1 plus x times, let's say 1 plus, so let's say times x cube. What is it? 怎么乘这个东西啊？假设我要用上面这个算法嘞 ，What do we have? We have x cube, we have x here. OK， 前面有什么东西？OK， 前面有什么东西？什么东西？Sorry，我觉得用另外一个 example 会比较好，给我想一下，用什么 example 会比较好一点 ？Maybe 用 x plus x square， maybe 2x square 会看得出东西。OK， 用这个 example 会比较好。Okay, so if using this example, what do you get? Get terms in x. You also get terms in x squared. Anything else? X cube also. That's all. Okay, good. So how do you figure out the coefficient here? So you need to add up all the possible product of coefficient such that when you multiply the monomial, x pops up. How many ways? Only one way in this case, 1 times x here. So in the CIBI there, you only got 1 times 1. Okay, but for x squared, how many ways to get x squared? Either you times x. Okay, so meaning 1 times 1, or you can get 2 times 1. Okay, and then third way is 1 times 2. So all together, what do you get? 2x plus sorry. 哎呀，不用哈啦，算错就讲算错了，哈个屁，就跟我讲，好像天塌下来一样，就讲错啊，it's OK 了，不用紧啊。因为我不会永远对的，你要知道，因为我都会错的。哎呀，而且我还经常错 ，OK， 所以你就讲吧，老师好像算错了就 OK 了，对，天不会塌下来 OK， 1乘1加2什么？3x square。Okay, but on the other hand, any hand or not? 应该没有 hand 了嘞。Okay. Sorry. So this one, yeah, right. Okay. So how about we compute the a of this version? Ax plus x squared plus 2x squared. We want to show that this is equal to a of 1 plus x cubed. Thank you. A of 1 plus x times a of x plus 2x squared. 是不是一样的算法哦？对吗？你觉得 ？What do you think? Is it the same calculation or not? Is it the same calculation? Is it the same calculation or not? Is it the same calculation? So you calculate the polynomial with x, calculate polynomial with a. It's literally the same. Okay, just that if you substitute a real number here, the real number here. So maybe 2. Okay, so you compute different way. Now here you just take 2 plus. So for example, let's just go down one more steeper step. So let's say a equals 2, you can see 2 plus 3 times 2 squared plus 2 times 2 cubed, which is equals to 1 plus 2 times 2 plus 2 times 2 to the 2. Okay. So you can see that in the real number calculation, these two ways of calculating is different, right? Okay, but if you do it in any variable, they look the same. Okay. Okay, so I mean, maybe that's why abstract algebra is hard, because you only can see this. This is already hard for you, but we can do even abstract. And in the real map, we are more abstract than this. Yeah. Okay, no. So this one is a kindergarten, right? 没有 kindergarten 太小了。A bit primary, secondary, L square, secondary, right? Okay. So now you do this. Okay, 然后你大学你学这个。Okay, after bachelor 你就更 abstract 一点。Okay. Okay 了。Okay. University maths must make sense at the secondary level. 所以如果你看不到这个，其实你要晚一些号码。OK 了。OK. Lastly, lastly, 最后一个是什么 ？A of identity is identity. Is it true? Why? Why? 1 in Rx is what? The constant polynomial. So if you evaluate your constant polynomial, what do you get? You always get 1. Okay, you always get 1. Okay. This is a 1 in R. Okay. Yeah, what time is it? Okay, good. So continue. Right. One more special substitution here. Let's say what's the example? So third example here. I think I messed up with my numbering. So let's put C here. So let's say we don't do real number substitution, we do complex. Okay, what happens if I do complex substitution here? What's the codomain? What do you think? What's the codomain I should pick? Sorry. Okay, so we should pick complex here because I send px to pi. Okay, substitute everything with I. Okay, so go back and check. Check that these satisfy ring homomorphism. Okay, check that this satisfy ring. Right. Next definition. So what's the thing we do after we introduce group homomorphism? Isomorphism, yes, good. So we also have ring isomorphism here. So basically it is just a bijective ring homomorphism. Okay, it's a bijective ring homomorphism. Okay, and if there's an isomorphism, okay, if there's an isomorphism between R and R prime, what do we say? We say that R and R prime are isomorphic. So similarly, I think we will denote the same way. So we just use the Kong. If you use latex a lot, it's a Kong. Is it Kong / Kong? Yeah, / Kong. R Kong R prime. Okay, Kong. Yeah, Kong. Yeah, 有很多情况都可以用，不一定是 isomorphic. So it's a Kong. Huh? Okay. Right. So you can also prove that ring isomorphism is a equivalent class. Okay, form equivalent relation. Sorry, form equivalent relation, and then you will have a equivalent class. Okay, before we jump to next part. Okay, before we jump to next part, let me ask you a question. Is a zero map a ring isomorphism or not? Okay, not isomorphism, but homomorphism. Is it a homomorphism? Zero map. Zero map. zero mat. Sorry, zero mat. Mob. So zero mat. So zero mat is what? Send everything to 0. Is it a ring homomorphism? Why? Good. So it's not a ring homomorphism because it sends 0 to it sends 1 to 0. But there's one case where this is a ring homomorphism. Unless what? Unless R prime is a 0 ring, where 1 equals to 0. Okay, no? Yeah. All right, good. Very good. Okay, we still got time. Let's go. So proposition 有一点点赶了，现在。So 没有道理也是很重要。你不明白这个道理，我也上不了这么快。道理很重要。Hi, substitution principle. So by this name, right, it means that you're gonna play around with substitution. So let's see how we play around with substitution here. So let phi be a ring homomorphism, and A, let alpha be an element in your core domain, this element. Then there exists a unique homomorphism. Okay, capital Phi from the polynomial ring of R to R prime here. So what do you think? What homomorphism I can put here? Nice user. How to go from a polynomial in X to R prime? So I give you a polynomial in X. How do you produce some element in R prime? What do you think? So I tell you one way to go from R to R prime, but I now want to go from polynomial in X over R to R prime. You already know how to go from R to R prime. How about the polynomial? How about the x's? Huh? How about the x's? Power of x. What do you think? Where can you send x? For example. Huh? You say louder. And try. Huh? Don't know. Okay, so I mean we fix an alpha here, so we can send x to alpha. Okay, so for example, if I do this, what it means? So 2x plus x squared, what happens? It will get sent to 2 alpha plus alpha squared. But really depend on how R sit inside R prime here. So in fact, you need the little phi of 2 here. Depends. Again, depends on this fact here. Depends on this phi here. Okay. Because you need to remember, we don't always work with the same ring. Yeah. So you need to depend on how you see this R in R prime here. Okay. The homomorphism here, we will phrase it as how we see this ring R inside R. So this is a map that we define on the generator that agrees with the map phi on the constant polynomials. Okay, so this is what it means. So agree with the map phi on the constant polynomial. So how you send 2 is by the little phi then. Okay, how you send 2 is by the little phi then. So you can do it more generally. Okay, you can do it more generally. So meaning you can consider multivariable. Generally. Okay, so you can consider multivariable here. So if you consider, let's say, alpha 1 up to alpha n in R prime, okay, then there's this unique homomorphism from how many function of variable here? You want to guess? S1 out to xn, okay, such that you just evaluate every xi to alpha I. Okay, also agrees with 5 on constant polynomial. Okay, so basically the little phi there will fix how the R coefficient gets sent to R prime. Okay. Okay or not? Should we do example first or should we do proof first? Okay. So let's try examples. Okay, if I do example later proof, you cannot sleep. Okay. So let's define a little phi from Z to FP. Still remember what this map is? Send n to n not p. Good. Not p. Right, so let's consider an example here. So let's look at a phi from Zx to sorry, let's say fp. Okay, so let's look at a specific phi here. Which phi I want to look at? Let's think about it. Maybe do a specific p. Let's do 5. Okay, so what do I want to substitute here? Maybe substitute with 4. Okay, so what happens if I do this? So this means that I will send x to 4 mod p. Okay, now let's look at a polynomial in zx. Maybe let's get some example from the audience, like yi heng, yi heng, yi heng ma, is yi hang, yi hang, huh? Okay, let's give me some elements in zx, z adjoint x. Give me some element in z adjoint x. What's the element in z adjoint x? Guess. If you don't know, guess first. I'll tell you wrong or false, true or false. X too simple. Give me longer a bit. 2x. Wait, this one longer, man. Give me more terms, Plus 1 One more term. 来一层，再一层，再加多一个 monomial 给我。来，给我一个 monomial。Next。哎，不要想这样久吧，给一个 monomial 吧。随便猜错也不用紧。来，给一个 monomial in x。x to the 什么 power？哎，怎么难以启齿的？选一个 power Power 2 Power 2 OK 咯。Okay, so let's pick some coefficient. 224这样大。Okay, so what's the image of this polynomial? Computer 自己写的。 自己承担。Okay. Okay. So before that, obviously, if you just substitute, you'll get these, right? So 2024 times 5 squared plus 2 times 5. 2 times 4, pick 4. And then plus 1. So if you do this calculation, what do you get? Before taking mod, before taking mod. Yeah, before taking mod. So what do you get? Okay, 那你用计算机。获利用计算机。考试不会出这种东西。说了？算出来了。32393. So this one is equals to what? Mod 5. Huh? 3 mod 5. Okay, good. But we can use another way to compute it, right? Because it's a ring homomorphism. So the other way to compute it is what? You can reduce your 2024 first. Correct or not? You can reduce your 2024 first, and then you evaluate x squared, and then you send 2 to mod 5. Sorry. And then you evaluate your, sorry, here is before evaluation is x squared, x plus 5 of 1. But capital phi of constant polynomial is what? It's a little phi. And then here is what? Just substitute x as 4. And then here is a little phi of 2. And then substitute x as 4. And then little phi of 1. But what is the little phi on 2024? It's 2024 mod 5. Okay, times 4 squared. And then 2 mod 5. 4 plus 1 mod 5. But if you do all the calculation, you just left with 4 times 4 squared plus 2 times 4 plus 1, everything mod 5. So here, what do you get? Plus 84, right? Okay, plus 8 plus 1 mod 算错了64 OK， 谢谢。我故意的，故意的。好，你没有听课。好，你没有听课。Okay, so if you do this calculation here, what do you get? Get 3 mod 5. 是不是 You see, if you understand it as a ring homomorphism, then you don't need to compute the long multiplication. You just reduce at every coefficient, and you can reduce at every substitution. Okay, yeah. 变小 p 变小 p 啊 Why? Because用错 phi 了 so it's a var phi. Why is it using a small phi for small phi here? Because remember that when we talk about evaluation polynomial, you have to agree with the map from the coefficient ring to the codomain ring on the constant polynomial. Okay, no. Look at here. If you just look at this evaluation map here, you see, there's no FP here, There's no FP here. But if you substitute X with something from FP, then X will make sense in FP. But how do you make sense of Z in FP? So somehow you need a map to tell you how to read Z in terms of FP. In this case, F5. Okay. Okay or not? So you need to be able to read everything inside a polynomial as a codomain ring. Okay. Yeah. So you need to know how your coefficient get read in terms of your codomain ring. Does it make sense? 明白吗？明白我讲什么吗？Okay, because You see the domain, codomain, no relation one. Okay, there's no relation. 没有关系的。But if you substitute x by some number in FP, 但是还有 z 嘞，你要怎样把 z 想成 FP？So I need to tell you a way。那个 way 是什么？那个 way 就是那个 ring homomorphism。How to read z in FP？z 被送去哪里 ？OK， 每个 z 被送去 FP 那个 FP codomain 的那里。OK，does it make sense？ 有问题吗？有问题吗？问题。Question? Okay, so let me think. So actually the proof is kind of boring. Let's skip it. I want to do more important stuff. Okay, let's skip the proof because the proof is actually captured inside these examples already. So if you go back and read the proof, it's actually these examples. Yeah. If I write it out, waste time. So go back and read the proof, and then that proof actually is describing these examples. Okay, describing by this. Yeah. Thank you. You are not wasting time. 可以，你叫环境卖 learning， 他很需要这个 learning， 他很需要。还要打。Okay. For the next part, I want to motivate from your high school algebra. Why? So let's motivate from your high school algebra here. So for example, if you look at this, what your high school teacher tells you, if you see this kind of expression. Factors, oh, right, factors, good. How to factors? Y plus x squared plus 1 times y squared. Okay, so there are two different ways to express this expression here. But in our sense, how do we say these two ways are different? So they really look different, right? But when they expand, they have the same terms. Okay, but how do we describe this phenomenon here? So for example, in this case here, we will say that the left-hand side polynomial, it lives in a ring adjoint x and y. So basically, you use x and y to build this ring now. But on the other side, how do we see it? We will see it as you will build this polynomial using coefficient using y, but coefficient live in Rx. Okay, so in high school, you didn't see that they are different. But in our case here, we'll see it differently. They live in a different ring. So the order of building this ring. Okay, so yeah, how can you work here? Yeah, that's the main. So later we'll establish the fact that these two rings is actually isomorphic. Ring is isomorphic, but they are not the same. I mean, in this case here, they are the same, but yeah, sure. After evaluation is the same, yeah. Yeah, after evaluation is the same. Actually, they are not just isomorphic, they're actually equal, actually. Later, we'll discover this fact here. So what's the difference here? So to be precise, what is R adjoint x1 here? In a step form, we will write these as a finite sum of xi, yi, okay? And then with coefficient aj, such that m is greater or equal to 0. And then all these aij live in your ring R. But on the other side, how do we describe this? These are all the polynomial only in the monomial of what? Monomial of y, I. Okay, such that what? This m is greater or equal to 0. And then ai will live in the ring of Rx. So this means what? The coefficient here is another polynomial. Okay, in the previous case, what are these coefficients? These coefficients are live inside the ring R. So in this case here, what is the coefficient? is 1. Okay, but on the other side, the coefficient is 1 and this x squared plus 1 here. Okay, or not? So this is the difference between R adjoint xy and Rx adjoint 1. Okay, or not? So you see Rx as a coefficient in this case. What? Before that. So in this notation here, R is a coefficient. In the other notation, Rx is a coefficient. Okay, like. Yeah. Maria, thank you. Very good observation here. So 我应该这样分。要不要救救我一下？啊？那今天随便你加了，不要管你。不用紧啊，没事啊。As long as this is finite 啊。OK， 我知道怎样做啊，我怎样救他了，我这样救他。不要有 m。And then this ij is less than some m。OK，这样应该可以。So 把它 fix m， 把它 fix 在大于等于0 ，and then ij 加在0跟 m 之间。Okay, I think this works. Okay, pick all the ij in between 0 and m, and then m could be large. Okay. So in English says what? The factorization in the polynomial is equivalent to the isomorphism in ring. 在上一个档次啊，如果你回去看中学的时候啊，原来你们是在做 ring isomorphism。You are guys just doing ring isomorphism here. Okay. Yeah. Okay. Let's prove this. This is quite useful to use. So let's give a statement here. Let's say. Okay, we do it even more general. So let x be a vector of polynomial here. Okay, so instead of just 1x, you have x1 to xm, and y is y1 to yn. We even do it more general. So let's denote it as a set of variables. And there's this unique isomorphism. What's this unique isomorphism here? If you look at a polynomial ring over these two set of variables, okay, and you regard all the s's, the polynomial in all the s's as a coefficient on variable y, set of variable y's, okay, then they're isomorphic. Okay, which is the identity on R. So you don't change your coefficient. I cannot call them coefficient now. So you don't change R under this map. Okay, so R stay the same. And actually you also sense the variable to themselves. Actually, this is not just isomorphism. This is also equality. But why we choose to call them isomorphism? 知道什么原因吗？等于跟 isomorphic 的差别在哪里？啊？等于 just says that every element on the left is equal to the element on the right. But isomorphism says more than that. It says that the structure is the same. Before you add, after you add, before you multiply, after you multiply. Okay, it's the same. Okay, so how to define this? How to prove this? So we're gonna use the substitution principle here. So before doing that, we will define. We'll define what? We'll define the inclusion map. Remember to use substitution principle here. We need the little phi here. So what's the little phi here have to do? The little phi here have to send R to Rx y. Okay, so you need to send the coefficient to the codomain here. Okay, coefficient to a codomain. But how to send it? I think it should be clear. You just send R to R itself. Okay, because this is what the question wants you to do. The proposition says, do identity on R. Okay, so you should send R to R. It works, it works, right? Is R an element of Rx, Y or not? It is, right? Okay, because it's a constant polynomial with coefficient R. Right, so by substitution principle, what do you have? The substitution principle tells you what? There exists a unique homomorphism, capital Phi from Rxy to Rx Ry. So what do you do here? So I already tell you how to send the coefficient. What's left to do is to tell you where I send x and y. So where should I send my x and y? I should send xi to xizers and then yj to yj. And so this is unique homomorphism. You only left to show it is an isomorphism. Why is it isomorphism? You need to show bijective. So to show bijective, what do you need to do? You can create a inverse, for example. How to create the inverse? Can you see that this is invertible? How? What's the inverse? Then xi to xi, yi to yj, and then r to r. Actually, it's exactly the same, but this isomorphism will tell you that the product structure also preserved. Okay. So hence, so I would say that so moreover, phi is invertible. So hence, required isomorphism is obtained. Okay. Right, just now I said that these two sets are equals, right? But really, they are equal when they are having this factorization here. But if you just look at a single element here, it really look different here, you know. It really look different. Okay. 其实不一样. Okay, actually it's not, it's actually it's different. Okay, actually it's different. So what this factorization doing is actually trying to describe this isomorphism here. Okay. Yeah, 为什么会可以做 factorization? You can do it also because of what? Why can you do it? Actually, here is because of distributivity. Okay. They are equal by distributivity laws. Okay, yeah. Actually, 他们是一样的，其实他们是一样。Yeah. 我之前那个 remark 有问题。Yeah. They are equal by distributivity law. OK 吗？有问题吗？啊？黑掉。好，现在54啊。Let me see 啊。Okay, finish 2 more corollary. I will let you go back. No more proof. Yeah. No more proof. 2 more corollary can go back. So corollary is division with remainder will also works for polynomials in 2 variables. How is it a corollaries? How is it a corollaries here? Okay, you know how to do division remainder with 1 variable, but how it works for 2 variables. And then this is a corollary, right? So meaning this corollary should follow from this proposition here. Okay. So how are you gonna use this proposition? So imagine this xy here is plain two variables here. You can regard it as a one variable polynomial with coefficient in another polynomial ring. So you can do division with respect to y first. Okay, no? And then you do division with respect to x. Okay, no? And then you can do one by one. So another corollary you want to guess or not? Yes, good. So you can do division with remainder with n variable because you can split out the n variable one by one, and then you use one variable division with remainder, and then you divide, finish that. But this is what you do in real life, right? Correct or not? Is this what you do in real life? 对吧？这是不是你在现实中生活会做的事情啊？可能有人的生活是这样，没有开玩笑。For example, let's take an example. Yeah. 喂，做么你们 ？Okay, let's take a quick example here. 讲完 corollary 再给一个 example， 不然不完整。等下你回家会睡不着。其实我睡不着。OK， 没事，你可以慢慢打。OK, so what to do here? 来，如果要除的话，怎么除啊？乱了啊。How to divide in this case? 有些人乘 x， 有些人乘 y， 有些人乘 z， 有顺序问题吗？没有 ，because they are all isomorphic. OK， 先做哪一个 ？OK， 有用没 ？OK， 我们来加一下，加一点。我说有错没？我等什么情况？哦 ，OK， 放上去，放上去。等，喂，冷静一点，冷静一点，没有笔，不要听话，冷静一点，冷静一点。怎么我错？OK， 我想太多了，我有一个 imaginary z。OK，then we can divide with respect to y square， 不是，对不对 ？So what can I do here? Minus x， 很恐怖合理吗？这个东西好像恐怖这样，这东西合理吗？没有，这个是加啦 ，sorry， 这样才对嘛？应该是减哦。这样东西好像看起来很恐怖这样的意思是说，它就是一个 remainder 啊，是不是？因为减来减去又是它，是吧？太乱说。好像算来算去又是回去啊，所以这是 remainder， 这个不够大。Okay, go back, give an example. We start next week. Okay, Tuesday. Let's give an example. Next week. 不够大，算来算去都是 remainder 来的这个。给我一个大一点的 example。我要不同的 variable 在里面。我这个degree 不够大，应该全部都不够大，所以就。 它这个里面要不大。模拟哦，那个模拟哦，那个模拟哦啊。I mean 这个那个，这个老外方的。对，要看两个。所以这边。
快你教我快把我的算。
这不能23223就是里面的了，除非你把这个改成3的话，123这样老师一个算错，就是123是吧？老师算错了，这不是吗
？X 对吗？
没有，完了，这个就是里面的了。
好像在循环。
没有，这个就是里面的了，这个就是里面的了。
快帮你写，里面的。
如果他出的东西，因为他现在这样子，他还是作弊嘛。如果像刚才这样呢，如果不要有3跟2，这样一定要打出哦。
什么东西？
不要有这2跟
同时 x y 在一起写哦
x y 在一起写。
这样
这样啊。
你刚刚跟我说的话说了一半没说完。
就是你不能用这一个方法去证，要用另一个
这么
证明这个 corollary。
什么方法？
我想的是重新定义什么叫做比它大的项，因为你得要，总之我可以写在这里。像这一个
假
，OK，
对，你
因为比如说因为举个x y 在这个里面啦，x 平方2x 平方 y 的 coefficient 是2x 平方。
对。
因为它的 leading coefficient 不是个 unit， 所以你不能用除法。
对，他刚才讲了，对，刚才讲，所以我刚才就想到，就是应该可能你只能够用那种这样的东西来除哦。如果这个情况的话，你只可以用这样的东西来除。
就是你也可以用回这一个，就是 x 的 a 次方 y 的 b 次方 z 的 c 次方这个东西来除的。不过你有一个要求，就是假如有另一个是 x y z alpha beta gamma，只要有任意一个 alpha beta gamma 是小过 a b 或者 c 的，这样子它就必须在里面的 term 里面。
它就会在里面的所以也是可以除啊，其实
也是可以除，
对啊，
也是可以
除，
也是可以除。就是你的里面的
term 跟你说的是你的那个证明的方法会有问题。
就是我还想问他这样子讲，它的里面的 term 包括什么 term？我只能讲
想一下，就证明觉得。
所以你刚刚那个例子的话，
没有，这个是因为纯粹就是他们的总 degree 好像小过。他们的总 degree 小过这边的，是吗？3、5、5、6、7、5、6、7、3、4、5、6。
他刚才想表达的意思
总
是说，
degree 小过，
所以不是总的 degree， 是要每一项的 degree 都不能。
因为你的 degree
每个都要超过。
你的 degree 小和大就定义就要换了，因为就举个例子，像是就是把它们加起来算 degree 了。比如说，
对，我刚刚其实一开始是在想 degree 的。
只要你一个小过就不是。
你这个时候
x y 的5次方，还有x y， 还有 x 5次方 y， 我可以讲 x y 的 degree 小过这个，我可以讲这个小过这个，但这两个是 incomparable， 没有办法比较哪个比较小，哪个比较大的。
等一下我试一下。你是说
能做到比 term 小的？
你说这个能不能够除这个？是不是你的意思？假设说的话，
对。
OK， 我假设说，其实那个 isomorphism 有顺序有关的，比如说你要先除 x 就先除 x， 先除 y 就先除 y， 但是它应该要等于 ，OK，try 先。假设我是对着 x， 对着 x 就除不了了，然后我就要对着5除。
对着5除是什么？
对着 l， 对着 y，
对着 y 也除不了，这个离定 term 这不是模拟 k 啊。
它的离定 term 不是。
你 x 5 y 5，你除非你 over x 哦。
也除不了，
这根本除不了呀。
没有，可以 y 5 over x 哦。
因为这个情况下哪个比例比较大就有点难讲。
有3个。
你要不要回去慢慢想一想？
回去慢慢想。OK， 你们要吃啊？
我只是觉得这个问题不是什么很短的时间内能让你想出来的。
我回去看一下这个 proof。
没有
下一次再给一个 example。
我觉得比较简单。
我也觉得。